us see this example where you need to solve x prime equals to this matrix that has a coefficient as fractions, right? So 5/4, 3/4, -3/4, and negative 1/4 x. And also given the initial condition is a 2, 3 at 0, okay? So what is the characteristic equation? Is lambda square minus the sum of these two. What is that? So 5/4 minus 1/4 is 4/4, that is 1 times lambda. So lambda square minus 1 lambda plus the determinant of this matrix. So 5/4 times negative 1/4 is negative 5/16. And then minus negative 3/4 times 3/4 will be negative 9/4. So minus negative 9/4 will be plus 9/4, right? Equals 0. So if you simplify, you will get lambda square minus lambda plus 1/4 equals to 0. So if you factorize this, we need two numbers whose sum is negative 1 and product is positive 1/4. That will be negative 1/2, negative 1/2, right? So lambda minus 1/2 times lambda minus 1/2 equals to 0. So lambda is 1/2 and 1/2. So repeated. It's two repeated eigenvalues, right? So the process is exactly the same. That's why I'm just doing it and then I'm showing you, okay? So for lambda equals to 1/2, how do I find out the eigenvector? Is AV equals to lambda V. This is A, that matrix A, times V. I am assuming V1, V2 equals to 1/2 is the lambda, right? And then V1, V2. If you simplify that, you will get, so 5/4 times V1 plus 3/4 times V2 equals to 1/2 times V1, right? And similarly, negative 3/4 times V1 minus 1/4 times V2 equals to 1/2 V2. So I'm taking the second equation, right? How do I do this? Is just I want to add 1/4 fourth V2 on both sides, 1/4 V2. So what do you get? You cancel out that, right? So negative 3/4 V1 equals to 1/4 times 1/2 will be 3/4, because this is like 2/4, right? 1/2 is 2/4 plus 1/4 will be 3/4 V2. So negative 3/4 V1 equals to 3/4 V2. So I multiply both sides by 4/3 or divide both sides by 3/4. You get negative V1 equals V2. If you take V1 equals to 1, you will get V2 equals to negative 1. So the eigenvector is 1, negative 1, right? So what is the solution? The first solution, I'm just denoting by superscript 1. So x is equals to e to the lambda t times the eigenvector. That's what you get, right? So we got the one solution. For the next solution, what you need to do is, for the next solution, you need to do a minus lambda I. We need to find out w, right? So such that a minus lambda I, w equals to v, that v, okay? So what is a minus lambda I? So 5/4 and then 3/4, right? And then negative 3/4 and then negative 1/4, right? And then minus lambda is what? Lambda is 1/2, right? Because that's a repeated one. So 1/2 times I is 1, 0, 0, 1. This is the identity matrix, okay? Times w. So this is like times, and then w vector equals to v vector, right? So what is v? It is 1, negative 1. Now we simplify the left side. What do you get? So you distribute this 1/2 to all of these. You get 1/2, 0, 0, 1/2, and then you subtract. So what you get is 5/4 minus 1/4, right? Sorry, 1/2. 5/4 minus 1/4. Sorry, 1/2 will be how much? So 1/2 is 2/4, right? 5/4 minus 2/4 will be 3/4, right? So you will get 3/4, and this is this minus that times that, and then 3/4 minus that will be 0. So it will be 3/4 again. Now how about this one? Negative 3/4 minus 1/2 times 0, right? That will be negative 3/4, right? And then negative 3/4 times negative 1/2 times 1. So sorry, negative 1/4 minus 2/4 will be negative 3/4. And then you get, let's say w is w1, w2. That's a vector, is equals to 1, negative 1. Okay, now, so how do I solve this? You will get 3/4 times w1, 3/4 times w1 plus 3/4 times w2 equals to 1. This is one way. And this is one equation. Another equation is negative 3/4 times w1 minus 3/4 times w2 equals to negative 1. This is another equation. Okay, so now you need to solve these two equations. Okay, and then so what do you get? So you can pick the first one or the second one, because you see that. So if you pick, you see that how do you solve these two? So basically you got the same equation from both of them, right? You get the same equation here. See, since you get the same equation for both of these, okay, so it is hard to solve. You see that, because there is a separate constant term there, okay. So you should assume certain values of W1 or W2 and then get the value of the other one. That is the only way, okay? So the easiest way is you can assume one of the either W1 or W2 is 0 and then solve for the other one. So what I'm going to do here is I want to, let's say, set W2 equals to 0. If you set this equals to 0 or that equals to 0, what do you get? You get W1 equals to, you get 3/4 times W1 equals to 1. So you get W1 equals to 4/3. So what is the vector W then? So the vector W will be 4/3 times 0. So you can assume any number you want to, okay? So that is still fine. All right. So what do you get? You got W, you got V, you got lambda. So hence, what do you get? Let me write x2 is equals to, the formula is t e to the lambda t is 1/2 t, and then v is 1 - 1, right? Plus e to the 1/2 t, and then w is 4/3 and then 0. So this is the second equation, okay? Or the second solution, I'm sorry. This is the second solution. So you can find out the Wronskian, you will get non-zero. Now I'm going to write down, I'm not showing that, so you can check yourself. Hence the general solution is, you can write x equals to c1 x1 plus c2 x2. This is what you get, okay? So what is c1 x1? C1 x1 is that one, right? So e to the 1/2 t, and then 1 - 1, that is x1, plus c2 times what is x2? X2 is that thing, right? So you can write t e to the 1/2 t, and then 1 - 1, right? And then plus e to the 1/2 t, and then what is that? 4/3 0, right? 4/3 0. And then that is the bracket there. So this is the final solution, okay? So sometimes, I want to tell you that sometimes you will get exactly the same vector here and here. In that case, you can combine to a single one, or you can just write that one and ignore that the second one, okay? You can do that too. So the final thing what I want to do is I want to see how would the direction field look like, because you see that what we get here is we got the eigenvalues both positive, right? So previously we had the eigenvalue both the negative eigenvalue in the last example, and we see that when we did the direction field, so it was like so stable proper node, meaning that everywhere it was like going to 0 0, right? For the stability of 0 0, for stability of 0 0, you can actually guess, right? As t tends to infinity, where does x goes? It sounds like x goes to infinity as well. Why? Because when t tends to infinity, this will be infinity. E to the infinity will become infinity, right? Similarly, this one, since that is positive, that eigenvalue is positive, it is going to the positive infinity. But if you want to see the direction field, what should I enter? 5/4 x, 5/4, and then x plus 3/4 y. That is the first equation, right? And then the second equation is negative 3/4 x, and then minus 1/4 y. That's what you get, right? You see that? Let me erase the let me see, where is the erase thing? Okay, let me erase all the curve, and you see that it is like going away from the origin, right? If you start here, it is going away, right? So wherever you start, it is going away from the origin, okay? So what we can see from here is if the eigenvalues are repeated but positive, right? If the eigenvalues are repeated but positive, the 0, 0 will be unstable. But there are two types of unstable. One is the unstable proper, and another is the unstable improper. So what decides that is, since the matrix A is non-diagonal, if the matrix A was diagonal, then that would be just like a star shaped going outward. Since it is non-diagonal, then you see that like it is like a spiral out kind of, right? Little bit spiral out. So you can see that if this matrix is non-diagonal, and if you get the repeated eigenvalues, but both eigenvalues have the positive sign, then you get the 0, 0 is unstable. We call what is the name? We call the unstable improper node, right? Unstable improper node in this case. Okay, it has given the initial condition, right? So the next thing I want to do is I want to use the initial condition there. So what is the initial condition? Initial condition is given as x0 equals to 2, 3, right? So let us do that. X0 equals to 2, 3. We have x0 equals to 2, 3. What do you get on this equation? You will get 2, 3. This is x, this is xt, right? So if you set that, you will get x0. If t equals 0, you will get x0 equals 2, 3 equals to c1, 1, negative 1, right? Plus c2, what happened? That will be 0. The first one will be 0 because this is 0 times, right? That will be 0. 0 plus that will be 4/3 0, right? So 4/3 0. That's what you get. So what do you get? 2, 3 is equals to c1, 1, negative 1 plus let me write down that negative 1 a little bit better. 1, negative 1, and then plus c2, 4/3 0, right? So if you do that, you will get 2 equals to c1 plus 4/3 c2, right? And then 3 equals to negative c1 plus c2 times 0, right? So c1 is negative 3. You see that, right? So c1 is negative 3. c1 equals to negative 3. And if you put that c1 negative 3 here, what do you get? So 4/3 c2 equals to 5, right? You get 2 equals to negative 3 plus 4/3 c2. What do you get? This is one value, right? And then you get 5 equals to 4/3 c2. So what is c2 then? c2 is 15 over 4. That's what you get. Hence the final solution is, is basically, you can find the explicit solution. I mean, you can find out the real solution. I mean, particular solution, because we know the initial values there, right? Is, you can write vector x, and then t is equals to c1 is negative 3 e to the 1/2 t 1, negative 1, right? And then plus, let me write on here, c2 is 15 over 4, right? And then t e to the 1/2 t 1, negative 1 plus e to the 1/2 t 4/3 0. So this is the final solution. Okay, guys. So this is how we solve a pair of first order linear homogeneous ordinary differential equation using the eigenvalue method when the two eigenvalues are repeated and the given matrix of the coefficient, matrix A, is non-diagonal. So it is a little bit longer, okay? So if you get that value of lambda negative, then you will see that it will be a stable improper node, meaning it kind of spiraled. It is not really spiral because we don't have the complex roots there, complex eigenvalues there, right? But we can see the shape similar to that, okay? For positive, it is unstable, and for negative, it is stable. Okay, guys?